On the last page of your notes, we have a section over calorimetry. And so this is really just our way of measuring heat transfer between a hot object and what I'll refer to as a cold object, but that doesn't mean that the cold one is necessarily cold. It just means that it is cooler than the hot object. So calorimetry is an experimental procedure used to measure the heat transfer from a hot object, and I'll color code these as well. I'll say hotter object to a cooler object. So, for example, if I had water that is at boiling temperature, which in Fahrenheit is 212 degrees, versus water that is just 200 degrees Fahrenheit, the boiling water would transfer its heat to the cooler water, but that doesn't mean that the water that's at 200 degrees is what we would actually consider cool. Because of the law of conservation of energy, the heat transferred from the hot substance must equal the exact same amount of heat transferred to the cold substance. Because of the law of conservation of energy, I'm abbreviating that as just capital E, the heat transferred from the hotter object must equal the heat transferred to the colder object. Or substance, whatever it is. So if we throw this back to our first page of notes, not getting confused with the colors, but just thinking about from a conceptual standpoint, what is happening to the heat? If something is releasing heat, if heat is a product, it is transferring its heat away from itself, the delta H sign is negative. If something is absorbing heat, then the delta H sign is positive. We are going to use that negative and positive to help set up our equation here, where I know that the heat that is lost has to equal the heat that is gained. So I'm going to show that by saying that the Q released, so the hotter object is going to release heat, or it's going to lose heat. So I'm going to say up here the Q, meaning the heat value, just like what we calculated on the previous page, released, or another way to say that is lost, is going to equal the Q absorbed. And it's going to be absorbed by the cooler object. So that's why I'm writing it in these colors. But what makes this make sense mathematically is that when you calculate the Q value of something that is being released, if I look at the one I just came from on this page, for example, in this one, question A, if energy is being released, then when you calculate your Q value, your Q is a negative value. So we are going to put that in our same equation. When you are absorbing, so this one, energy is needed, it's absorbing energy, it's a positive value. Or same thing with this one, it absorbs it, it gave me a positive value. So being consistent with our signs, this tells us that the negative Q value of the released, or the substance that releases its heat, is going to equal the positive absorbed. This makes it make sense later on when we actually get to calculations, so don't overthink the positive negative at this point. But another way that we'll write this is that the Q of the hot object, or the negative Q of the hot object, is equal to the positive Q of the cooler object, where your Q value is calculated the exact same way that we did on the previous page. Heat will always move from the thing that has more heat to the thing that has less heat, so it always moves from the hotter object to the cooler object until thermal equilibrium is reached. What that thermal equilibrium is talking about is that means that at the end of your heat being transferred, at a certain point, enough heat will have been transferred that the hot object cools down enough and the cool object heats up enough that they are at the same temperature, and that's what we refer to as thermal equilibrium. So this means that both substances, so both are at the same